Hello, and welcome again to Chapter 14. I left off on df over d volume equals epsilon del dot e times e plus e dot del times e plus 1 over mu times the same thing for the B field minus 1/2 grad epsilon e squared plus 1 over mu b squared minus epsilon mu change of Poynting vector with respect to time. So from this point, I'd like to introduce Maxwell's tensor formula. T sub I sub j equals epsilon E sub I times E sub j minus 1/2 Kronecker delta dependent upon I and j times the magnitude of E in all directions squared plus 1 over mu times the same thing for the B field. Now, we can say these two are equal by taking the divergence of T. When we do that, we say that derivative of force with respect to volume is equal to del dot T minus E mu times the change of Poynting vector with respect to time. We multiply both sides by d volume, and it cancels over here on the far left. And we take the integral. Integral df equals integral of del dot T dv minus epsilon mu, the change of Poynting vector with respect to time, times dv. Now this middle term, the integral of del dot T dv, should look familiar because it is the other side, or one side, of the divergence theorem. So we can change it, but to make it a little bit easier, to read force times force in the I direction is equal to the integral T sub I sub j times dA sub j minus the change with respect to time times the integral of the Poynting vector divided by c squared dv. We get the c squared from epsilon and mu. So, how do we work these matrices? Easy. So, row 1, column 1. It is I in the x direction and j in the x direction. The j terms determine the columns, and the I terms determine the rows. So when we work this out, we take the tensor formula here that I introduced to you and say that we put the i's in the x and j's in now the x direction. And we say that epsilon sub epsilon times e sub x times e sub x minus 1/2, where the Kronecker delta is 1. Now, let me step back and say that the Kronecker delta is only 1 whenever j is equal to I, and the Kronecker delta is 0 when j does not equal I. So the Kronecker delta is only going to be 1 at locations such as x, x, and y, y, or row 1, column 1, and row 2, column 2. I'm leaving out the B field this time, and the x component as well. No, I'm sorry, the z component. We're leaving out the z component to make this just a 2 by 2 matrix. Not very long. So, in order to work this out, we say that we plug in x for I, and this time x for j, minus 1/2 e sub x squared plus e sub y squared. So we get e sub x squared from these two terms minus 1/2 e sub x squared from this. And we bring that over here to the matrix, and that's what it ends up being equal to. And it would work out the same thing if you had a B field as well. Now, row 2, column 2, I'm sorry, not row 2, column 2, row 1, column 2, x and y, I and j are not equal. I is x and j is y, so the Kronecker delta is 0. And we get e sub x times e sub y minus 0. No magnitude is in this. So our answer is simply epsilon times e sub x times e sub y. And the same thing works out that way for e sub y, row 2, column 1. And so I'll work it out. I is equal to y and j is equal to x. And you just get epsilon times e sub y times e sub x. Now lastly, row 2, column 2, row y, column y, we get e sub y squared from these two terms minus 1/2 times the magnitude. And these two being squared, it's the same thing as saying 1 minus 1/2 in the y direction. So the x is left as a negative value. The x component is a negative and the y component is positive, where otherwise the x component was positive in row x, column x. And same thing if we had a z direction. It would be positive e sub z, and these two terms would be negative. Anyway, thank you very much for your time, and that is how to work out the Maxwell tensor matrix.